Chapter 1, Section 6, Resting Membrane Potential. The resting membrane potential is the potential difference that exists across the membrane of excitable cells, such as nerve and muscle, in the period between action potentials, in other words, at rest. As stated previously, in expressing the membrane potential, it is conventional to refer to the intracellular potential relative to the extracellular potential. The resting membrane potential is established by diffusion potentials, which result from the concentration differences for various ions across the membrane. Recall that these concentration differences have been established by primary and secondary active transport mechanisms. Each permeant ion attempts to drive the membrane potential towards its own equilibrium potential. Ions with the highest permeabilities or conductances at rest will make the greatest contributions to the resting membrane potential, and those with the lowest permeabilities will make little or no contribution. The resting membrane potential of excitable cells falls in the range of -70 to -80 millivolts. These values can best be explained by the concept of relative permeabilities of the cell membrane. Thus, the resting membrane potential is close to the equilibrium potentials for potassium and chloride because the permeability to these ions at rest is high. The resting membrane potential is far from the equilibrium potentials for sodium and calcium because the permeability to these ions at rest is low. One way of evaluating the contribution of each ion that each ion makes to the membrane potential is by using the chord conductance equation, which weighs the equilibrium potential for each ion, calculated by the Nernst equation, by its relative conductance. Ions with the highest conductance drive the membrane potential toward their equilibrium potentials, while those with low conductance have little influence on the membrane potential. An alternative approach to the same question applies the Goldman equation, which considers the contribution of each ion by its relative permeability rather than by its conductance. The chord conductance equation can be written as follows. E sub m, which is the resting membrane potential, equals the ratio of the conductance for potassium to the total conductance times the equilibrium potential for potassium added to similar terms for all of the other permeant ions, in this case sodium, chloride, and calcium. In this equation, E sub m is the resting membrane potential expressed in millivolts. G sub k, as well as for all the other ions, is the conductance for K, or for whichever ion it's referring to, which is the reciprocal of resistance. G sub T is the total conductance. E sub k, and for all the other ions, is the equilibrium potential for that particular ion expressed in millivolts. At rest, the membranes of excitable cells are far more permeable to potassium and chloride than to sodium and calcium. These differences in permeability account for the resting membrane potential. What role, if any, does the sodium-potassium ATPase play in creating the resting membrane potential? The answer has two parts. First, there is a small, direct electrogenic contribution of the sodium-potassium ATPase, which is based on the stoichiometry of 3 sodium ions pumped out of the cell for every 2 potassium ions pumped in. Second, the more important indirect contribution is in maintaining the concentration gradient for potassium across the cell membrane, which is then responsible for the potassium diffusion potential that drives the membrane potential towards the potassium equilibrium potential. Thus, the sodium-potassium ATPase is necessary to create and maintain the potassium concentration gradient, which establishes the resting membrane potential. A similar argument can be made for the role of the sodium-potassium ATPase in the upstroke of the action potential, where it maintains the ionic concentration gradient for sodium across the cell membrane. That concludes Chapter 1, Section 6.